This is Calculus Base Physics 2, and we're in Chapter 25, Working Problems. And the first problem we're going to look at is number 8. Okay, so I'm in the right book, I'm in the right chapter, I'm looking at number 8. A bird stands on a DC electric transmission line. Now, where in the world are we going to find a DC electric transmission line? Well, it turns out we're going to find them in our wind-powered stuff, because the wind energy people like DC. And the line is carrying a current of 3,100 amps, and the line has a resistance of 2.5 times 10 to the minus 5 ohms per meter. And the bird's feet are 4 centimeters apart. And we want to know what the potential difference is between the bird's feet. Okay, well, there's only one formula that's worthwhile, and that's V is equal to IR. And we know the current, and 3,100 amps, and we know the resistance, 2.5 times 10 to the minus 5 ohms per meter, and we know how many meters we have, 0.04 meters. So meters go away, amps and ohms give me volts, and I throw that in my calculator, and my calculator says 3.1 millivolt. And then I ask myself, how many significant digits? And I only have 2, and my answer is in 2, so I am happy with that. What happened? No integration or anything? Something's wrong with that one. Number 14. Can a 2.2 millimeter diameter copper wire have the same resistance as a tungsten wire of the same length? Can it have it of the same length? And the issue would be, well, yeah, it could. It's just a matter of what size the tungsten wire is. Give the numerical details. Okay, so we're gonna use equation 25-3, and we're gonna need the resistivity of copper, and we're going to need the resistivity of tungsten. Does anybody remember the chemical symbol for tungsten? Is it Ti? No, that's titanium. What is it anyway? Is it W? Yeah, it's W. Okay, so that's fine. And for copper, the resistivity is 1.68 times 10 to the minus 8 ohm meters, and for tungsten it is 5.6 times 10 to the minus 8 ohm meters. Okay, so I guess what we need is something for the area. So the area is pi r squared, or pi d squared over 4. We could go either way. So the resistance of the copper wire is going to be rho length divided by area, which is going to be rho 4L over pi d squared, because the 4 goes up on top when I divide it by whatever it is, and so that'd be the rho resistivity of copper. And then the resistance of the tungsten would be rho 4L over pi d squared. All right. And we want those two to be equal. We want the resistance to be equal. Okay, so rho W is rho copper. And by the time we get rid of all the things that are the same, everything's the same except for the length is the same. All right, so I'm going to have rho tungsten divided by d squared of the tungsten is equal to rho copper divided by d squared of the copper. Okay, well that seems reasonable. Okay, so I know the diameter of the copper. I want the diameter of the other guy. So d tungsten square root of, okay, that one over there, this one over there, d squared of the copper, rho tungsten, rho copper. All right, and the d squared of the copper can come out. Okay, so the diameter of the other wire, diameter copper, square root of the resistivities. All right. We want the diameter of the copper to be, well, it doesn't really matter because all the things go away. Okay, so we'll call it 2.2 millimeters. And then this guy becomes dimensionless, 5.6, 10 to the minus 8, 1.68, 10 to the minus 8, and we get the diameter is going to be 4.0 millimeters. If I could spell millimeters. Well, that was cool. All right. Now we're going to do number 22. A small rectangular solid made up of copper, not carbon, has sides of 1, 2, and 4 centimeters, lying in the X, Y, and Z direction, and we have a graph below. Okay, so we'll do the graph thingy. And now who put Z in that direction? I mean, come on, guys. You know better than that. This is a physics class. Z is supposed to be going up. Alright, so we have something that looks like. Oh, that's just such a wonderful drawing. 2 centimeters in the Y direction. 1 centimeter in the X direction, and 4 centimeters in the Z direction. Okay. Current is passing, determine the current, the resistance for the current passing through it in the x direction, the y direction, and the z direction, given that resistivity for the carbon, 3.0 times 10 to the minus fifth ohm meters. Okay, so we want resistance in the x direction. And using equation, we're going to use equation 25-3. We find that that's rho, length in the x direction, area in the y-z direction, because that would be the area we'd be dealing with. Okay, so that being the case, 3.0 10 to the minus 5 and the length would be 1 times 10 to the minus 2 meters, and the area would be 2 times 10 to the minus 2 meters times 4 times 10 to the minus 2 meters. Changing my centimeters to millimeters. Okay, so that being the case, we will throw it in our calculator and say in the x direction, we're going to have 3.8 times 10 to the minus 4 ohms. Okay, now we're going to look at resistance in the y direction. So I want rho, length in the y direction, area in the xz direction. I'm going to have 3 times 10 to the minus 5 ohm meters. I'm going to have y direction is 2 centimeters, 2 times 10 to the minus 2 meters. And I'm going to have 1 times 10 to the minus 2 meters times 4 times 10 to the minus 2 meters to be my area. I'm going to put it in my calculator, and my calculator says 1.5 times 10 to the minus 3 ohms. Okay, and then we're going to look at resistance in the z direction, rho, length in the z direction, area in the xy direction, 3 times 10 to the minus 5th ohm meters. In the z direction, we have 4 centimeters, 10 to the minus 2 meters, and then dividing by 1 centimeter times 2 centimeters. Put that on my calculator, and I find that R in the z direction is 6 times 10 to the minus 3 ohms. In all cases, that isn't a whole heck of a lot. Not very many ohms at all. Okay, number 28 is next. I have a filament in a light bulb. The resistance of the filament we want to has a resistance of 112 ohms at 20 degrees Celsius and 150 ohms when hot. Isn't that convenient? Now, what does hot mean, I wonder? That's a good question. But it says look at problem 19, so I'm going back and looking at problem 19. And in 19 we're supposed to come up with that temperature. And yeah, I'm thinking that we should go well, I'm not so sure that we have to go back to 19 to know what hot is, as in problem 19. So in problem 19, we do have to come up with alpha, which isn't given us in this problem. So alpha is equal to 0.0045 per degree centigrade. So that might be the only thing we have to get from 19. Calculate the temperature of the filament when it's hot, and take into account the change in length and area of the filament due to the thermal expansion. Use tungsten, for which the thermal expansion coefficient is 5.5 times 10 to the minus. Alright, so so we want to use a different alpha. We want to use an alpha 5.5 times 10 to the minus 6 per degree Celsius. We're not using the one from problem 19. Okay, so we're going to do the A part first, and then we're going to do the B part. Alright, so the resistance at the lower temperature. Okay, so the resistance at the lower temperature, and we'll just use a 20 degree there. The resistance at 20 degrees is rho length area. Okay, and we found out before that that's rho length 4L over pi diameter squared. Okay, so we got that from the last problem. And alpha is going to be our coefficient of resistivity, and we're going to use alpha T. We're going to use alpha T for our thermal expansion coefficient, and we'll look at the problem again. Okay, so this guy is the expansion coefficient, and we're going to keep this alpha is correct, because this is the alpha due to the thermal effect on resistance. Okay, so now we have our act relatively together. Okay. All right, well, that being the case, the resistance when I'm hot okay, so this is rho at 20 degrees, rho at 20 degrees, length at 20 degrees, length at 20 degrees, diameter at 20 degrees. All right. And now if I look at the resistance when I'm hot, that's going to be rho naught, rho at 20 degrees, times 1 plus alpha my delta T times 4, the length naught, times 1 plus thermal expansion delta T divided by pi d at 20 degrees, 1 plus alpha T plus minus T at 20 degrees. That would be, and this guy has to be squared. Okay, so that's what we're going to do, and going to do that. So we're going to manipulate this guy a little bit and say that that's the rho at 20 degrees, 4L at 20 degrees, pi d at 20 degrees squared. And then on the top, we're going to have 1 plus alpha alpha 1 minus, we can put a 20 in there, 20 degrees, divided by, that's this guy, and then I'm going to get rid of the squared guy on this side, and have 1 plus alpha T minus 20 degrees. Okay, and we recognize the rho at 24, L at 20, whatever. We recognize that as all of rho at 20. This guy here. Let me move that up a little bit. Okay. We recognize that is sitting right there, and the resistance at 20 degrees is 12 ohms. So we can put in 12 ohms. So resistance hot is going to be 12 ohms times 1 plus alpha T minus 20, 1 plus alpha T minus 20. Okay. And we know the resistance when it's hot. Do we not? Yes, we do. We know the resistance when it's hot. So we can put in a 140 is 12. 1 plus alpha T minus 20. 1 plus alpha T minus 20. And now the only unknown we have in the equation is the temperature. Okay, so we can go and rearrange all these things and see if we can come up with a temperature. So we're going to cross multiply and multiply by this guy, and we're going to have the temperature equals to 20 degrees, the original temperature, plus the resistance hot minus the cold resistance divided by the cold resistance times alpha minus the hot resistance times alpha T. And so that would be fine. And then we put in the values for alpha T, put it in my calculator, and we have 20 degrees centigrade plus 2,405 degrees centigrade, and we end up with a final temperature of about 2,400 degrees centigrade because we only have two significant digits. Okay, well, that did well there. Part B. Part B. In this temperature range, what is the percent change in resistance due to thermal expansion, and what is the percent change in resistance due solely to change in rho? Alright, so we want to know the change just due to rho and the change just due to thermal expansion. Okay, so we go back in our formulas and we find the formula that says has both length and diameter in it, and that would be the thermal equation. Okay, so I got R over R at 20 degrees is equal to rho at 20 for length pi d squared, and without the subscript I'm hot, rho at 20 for length naught pi d naught squared, and that's going to be L divided by L naught d, that's 20, d at 20 squared divided by the hot temperature squared. Alright, we substitute back into that equation and we get that L naught times 1 plus alpha t, t minus t at 20, and this is at 20, over L at 20, times d at 20 squared over, see if I can make it all fit, d at 20, 1 plus alpha t, well, we'll just put in a delta t, squared, that guy's squared, and then I can get rid of some of these guys and I can have 1 over 1 plus alpha delta t, delta t, and I put in the numbers for those guys and I end up with 0.9869. And then I ask myself, what is the percent change? Alright, so this is R over R naught caused by the only the change, the expansion of the metal. Alright, And percent change is going to be R minus R at 20 divided by R at 20 times 100. And the change due to, so that's going to be R over R at 20 minus 1 times 100. So I'm going to have 0.9869 minus 1 times 100, and I'm going to get minus 1.3%. The percent change only due to thermal expansion. Then I go back and continue and ask myself, well, what is the change due to resistance? Alright, so I'm going to do the same thing again. And I'm going to look at the resistivity change only, and I look at R over R20, and I end up with rho 4L D naught 20 divided by rho 20 4L 20 over D 20 squared, and that's going to be rho over rho naught when I get done, because those are the only things that require that change, and that's going to be rho naught 1 plus alpha delta T divided by rho naught, and we'll make that a rho 20, 20, and 20, so we're protecting our subscripts. That's going to be 1 plus alpha delta T, 11.82. So R over R0 is 11.82. Doing the same thing again, R over R0 minus 1 times 100%. We end up with 1,082%, but clearly we don't have that many significant digits, so we're going to call it 11,000%. So 11,000% of the change is caused by the resistivity change, and a very small percent, and it's going the wrong way, 1.3%, is changed by the dimensional change by itself. Well, that covered a lot of Physics 1 stuff there, if I ever saw it. Okay, now we're going to look at number 36. Oh, good. I got a hair dryer. It has two settings. So I have 120 volts, and I have the 850 watt setting, and I have the 1250 watt setting. And the question is, at which setting do you expect the resistance to be higher? We have to make a guess first. Alright, so I'm going to guess. I'm going to guess the 1250, because though power is higher, I'm going to guess the resistance is higher. Okay, so that's my guess. Now I'm going to have to calculate something. So power is voltage squared over R, which means resistance is voltage squared over P, which means resistance is proportional to 1 over the power, which means my guess is wrong. That means that the guy with the least power will have the most resistance. Therefore, the 850 watt guy has most resistance. Okay, now we got to do the B and C part, find the resistance. Okay, so the B part wants to know resistance at, well, resistance is going to be V squared over R, 120 volts squared, power, not R, divided by 850, and we end up with 17 ohms. And the resistance is still V squared over the power, 120 volts divided by squared, that is, divided by 1250 watts. And I end up with 12 ohms. Okay, so that's 36. Moving on to number 44. An extension cord made of 2 wires of diameter 0.129 centimeters, which is number 16 copper wire, and a length of 9 feet, 2.7 meters, is connected to an electric heater that draws 15 amps on a 120 volt line. How much power is dissipated in the power cord? Okay, so power is going to be I squared R. We're going to use equations 25.7a and equation 25.3, in case anybody is wondering. Alright, so that's going to be I squared rho L over A, which is going to be I squared rho 4L over pi d squared. Alright, so now we're going to come up with power. This is power due to heat loss. I squared R is heat loss, and we'll be using that often. Okay, so I've got 15 amps squared, resistivity of copper 1.68, 10 to the minus 4th ohm meters. 4 is 4. The length. Well, I have 2 wires, one coming and one going, and they're both going to have the same current going on them, so I better use twice 2.4. So 5.2 meters is my length divided by pi, and the diameter, I need the diameter to be in meters, 0.00129 meters squared. And that meters looks pretty funny looking, doesn't it? So, okay. I have meters squared, I got meters, 2 meters on top, I got ohms left over, I squared R. Okay, so my dimensional analysis is correct. I put it in my calculator and I get 15.62 watts. And then I say, I don't think so. I only have, well, I have 3 significant digits everywhere except the length and the voltage. So, all right, well, that's 2 out of 2. So I'm going to go with 16 watts as the power being dissipated, just because I'm using an extension cord. I'm going to look at 48 next. I have a 1 meter long wire that's at a temperature of 3,100 K. So I got 1 meter is my length. I have a temperature 3100 K. I've got a current. I don't know why I'm writing these things backwards for. I haven't figured that out yet. 15 amps flows through it. What is the diameter of the wire? Assume the wire loses energy only by radiation, and the elasticity is 1.0. And the surrounding temperature is 20 degrees centigrade, which is 293 K. And there's a hint here, says look in section 1910 for any help that you might need. Okay. So that being the case, we're going to go and look in that section. We're going to find that we're going to need to use equations 25-7a and equation 1918 and also equation 25-3. So those are the equations we're all bringing together, and we're going to say, well, I squared R is my power loss, and that's going to be the elasticity times sigma times the area times the temperature of the high guy to the 4th power minus the temperature of the low guy to the 4th power. Okay, so now we're going to go and manipulate that sum I squared. This is 4 rho length divided by pi diameter squared is equal to elasticity sigma pi d L. Pi dl is the area of the wire, the outside area, the surface area that's emitting the heat. Pi dl, pi d is the diameter, L is would be the surface area of the cylinder. T to the 4th high minus T to the 4th low. Okay, well, that being the case, I can get rid of a D, I can get rid of an L, and I can solve the equation for D. So if all I do is get rid of a D, I have D squared over here, and that gives me D cubed. Okay, so I'm going to say D is equal to, and whatever I do, it's going to be the cube root, 4 I squared rho divided by pi squared E, elasticity sigma temperature high to the 4th minus temperature low to the 4th power raised to the 1/3 power, because I got a D cubed sitting there. Okay, so now we can put in all of our numbers, and I've got 4, 15 amps squared. Rho is 5.6 times 10 to the minus 8. For the metal that I have, pi squared 1.0 for the elasticity 5.67 times 10 to the minus 8th watts per meter squared Kelvin squared times 3100 to the 4th minus 293 to the 4th. The entire thing raised to the 1/3 power. Okay, now assuming you can put it in your calculator and get the right answer, you'd get 9.92 times 10 to the minus 5th meters. But normally a diameter we'd express in millimeters, so we'd call it 0.099 millimeters. And is that what we're trying to find out? 48. What diameter of wire is being used? Okay, so there we go. That's the diameter of the wire being used. Number 56 is next. And in number 56, we're going to go use an integral in on page A7 of appendix B4, and just something that we're going to have to go do. Alright, so 56 for a time-dependent voltage V of t, which is periodic with period t, the RMS voltage is defined as, alright, so voltage RMS is equal to 1 over t, integral 0 to t, V naught sine 2 pi t, little t, over period squared dt square root of. Okay, that's fine. Use this definition, and knowing that the peak voltage is V naught for a sinusoidal wave, V of t is equal to that from blah 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 blah. What are we supposed to be showing? Then we do it again for a positive square wave. Okay, so we'll do it for the sinusoidal wave first, and we're looking for the RMS voltage. Okay, well, that means all we have to do is just do this integral. And so now it's time to look at appendix A, page A7, and appendix B, 4B, and we see the sine squared of AX. Alright, so we see the sine squared of AX, which is what we have, is equal to x over 2 minus sine 2AX over 4A. Okay, so that's the integral we're going to use. Third one up from the bottom of B4. Okay, so that's what we're going to do. The V naught can come outside, so I got V naught over t, and I've got the integral of sine of a t quantity squared is what I'm going to end up with. So I'm going to have t over 2 this is squared because that's squared there. So I'm going to have t over 2 minus sine 4 pi t over 8 pi divided by t, evaluated at 0 and t, and we want the quantity of that squared, square root, quantity of that square root. Okay, I guess that's what we got to do. V naught squared over t. I put in a t. I get a t over 2 minus sine 4 pi t, which is the period, over 8 pi over t minus t, doesn't look like a t to me, minus 0 over 2 minus the sine of 0, which is also 0, and the whole thing is raised to the 1/2 power. So it looks like the bottom end is going to be like so, and so I've got looks like I've got a t there and a t here and a t there that all cancel out. So it looks like I have and guess what? The sine of 4 pi t, where t is the period, is going to be 0. So I end up with v naught squared over 2, the square root of, so I end up with v naught divided by the square root of 2. So the A part says that the RMS voltage, voltage RMS for a sine wave is going to be v naught divided by the square root of 2. Isn't that lovely? Now we're looking at the B part. And in the B part, we have a positive going sine wave. Okay, so I'm going to have V of t is going to be equal to V naught when 0 is less than t less than or equal to the period over 2, and it's going to be 0 when I'm t over 2 less than or equal to t less than or equal to the capital T guy. So I got something, I got a wave that looks like that. And that's my period t. Okay, that being the case, we want, by definition, we want the RMS voltage to be 1 over t, integral 0 to t, v squared dt raised to the 1/2. Okay, so I'm going to have 1 over t integral 0 to t over 2 of v naught squared dt plus 1 over t integral t over 2 to t of 0 squared dt, and when we get done we want to raise it to the 1/2 power, take the square root of it. This guy over here looks pretty much 0. So we can get rid of him. And on the other side, we have 1 over t, and we've got v naught squared t, evaluated at 0 and pi over 2. When I put in a 0, everything is 0. When I put in And we forgot to do the 1/2 thing, power to the 1/2. Okay, when I put in the pi over 2, I get V naught squared over 2 minus 0 raised to the 1/2 power. And I get V naught divided by the square root of 2 again, twice in a row. So voltage RMS, whether it's a square wave or whether it's a sinusoidal wave, is going to be V naught divided by the square root of 2. Okay, I'm going to do problem number 58. A 5.8 meter length, L 5.8 meters of diameter wire 2.0 millimeters carries amperage of 750 milliamps of current when the voltage is to 22.0 millivolts is applied to its ends. If the drift velocity is, drift velocity is that a J? Is that what drift velocity is? 25.8. Yep, J. J is the drift velocity. Okay, so where was I? 28. If the drift velocity J is 1.7 times 10 to the minus 5 meters per second, determine the resistance of the wire, the resistivity of the wire, the current density in the wire, the electric field inside the wire, and the number of free electrons per unit volume. Okay, well, if they can write it down and it's in English, we ought to be able to do it. So I'm looking at A, and I remember that V is equal to IR. And I'm supposed to calculate the resistance of the wire. So the resistance has to be V divided by R, V divided by I. And the voltage was 22.0 millivolts, and the current was 750 milliamps. Therefore, my resistance had better be somewhere around 0.029 ohms. Okay, well, we got the A part done. B part. We have to calculate the resistivity. So we remember that resistance is rho L over A. Rho, if I rewrite, I have rho is equal to RA over L, and my area is going to be pi R squared over L. Okay, so the resistivity is going to be my resistance, which I just calculated, 0.029, and I'm going to keep some significant digits that I threw away in the other answer, times pi times my radius. Okay, so I have a diameter that's 2, so my radius is 1, So that'd be 0.001 meters squared divided by the length, 5.8 meters. So I put those in my calculator, and I come up that my resistivity is going to be 1.6 times 10 to the minus 8 ohm meters. Okay, well, that is that part. The C part, I want to calculate the current density. So I'm going to go to equation 2517, which we haven't used yet, and find that, no, I'm going to use 2511. 2511, and I'm going to find that the drift, what's it called? The velocity drift divided by I over A is equal to I over A. That being the case, we can calculate, what are we calculating for C? The current density, amps per meter squared is what we're looking at. And so that's going to be I divided by pi r squared, which is going to be 0.75 amps divided by pi times 0.001 meter squared. So the current density is J. All right, the drift velocity is Vd. So we're going to move back up, and we're going to change this to Vd. That's better. Now I feel happier about that. Okay, so I'm going to end up with my current density of 2.4 times 10 to the 5th amps per meter squared. Okay, then I'm going to look at the D part of the answer. I want to find the field inside the wire, the electric field inside the wire. So I go to equation 2517, and I find that J is equal to 1 over rho E, and E, current inside the wire, is going to be rho J. Okay, I know rho because I already calculated. Good thing they gave me these in the right order, otherwise I would be difficult to do. Normally the author will do that. He'll put these in a different order, so it's impossible to do. 2.387 10 to the 5th amps per meter squared, and I end up with 3.793 10 to the minus 3rd volts per meter. And then I say, well, I really only have two significant digits, 3.8 times 10 to the 3rd volts per meter. Right, now we're looking at the last part, the E part, which wants to know the number of free electrons per unit volume. Okay, so we're going to use equation 2514, and we're going to say the current density is the number of the electrons I have times E V D, and the number of electrons I is going to equal to J divided by E VD. Alright, so I've got 2.387 10 to the 5th amps per meter divided by amps per meter squared divided by 1.7 times 10 to the minus 5 meters per second times 1.6 times 10 to the minus 19th coulombs per electron, and I end up with the number of electrons being 8.8 times 10 to the 28th electrons per meter cubed. Okay, and is that the last one I'm doing? Yes, it is. That ends chapter 25.